So for this part, what we will actually do is to um, have a method in integrating definite integrals or indefinite integrals. And the method is called the substitution rule. Okay? And I have shown you this before. Okay? These are the indefinite integrals that we know as of this moment. Okay? These are the indefinite integrals we know as of this moment. So, we will have more. We will have more. We will add some more formulas in this list here. And to do that, we will need this method, the substitution rule. So what is this substitution rule? Let's start with the following. Let us consider the integral of 1 plus 2x dx. So for this, let's practice our integration. For this, we can just integrate this directly. So integral of a constant, it's just your x, because again here this is 1, so it's 1 times x to the 0. So if we apply the formula, we will have x to the 0 plus 1 over 0 plus 1, and therefore we'll just have x. And then for this guy here, it's 2x raised to 1 plus 1 divided by 1 plus 1 plus the arbitrary constant. This is now x plus x squared plus the arbitrary constant. So this is the integral of 1 plus 2x. Easy peasy. This is our just usual way. Suppose we consider this. We now have 1 plus 2x squared. Well, one way, without using an unusual technique, quote-unquote unusual, what we can do is to expand this 1 plus 2x. We can rewrite this as, if you expand this 1 plus 2x squared, you will have 1 plus twice the product, 1 plus 4x plus 2x squared. So we have 4x squared here, dx. And then we can just do the integration. So if we integrate this, we will have here x plus 4x squared over 2 plus 4x cubed over 3 plus the arbitrary constant c. And this is just x plus 2x squared plus 4/3 x cubed plus c. And this is our answer. But what if we have this? 1 plus 2x raised to 100. Are you going to expand this? That's a bad idea. Or what if we have the sine x, integral of sine x? We know this is negative cosine x plus c. Correct? Using our formula. Is it negative cosine x or positive cosine x? So it's negative cosine x. But what if we have this sine 2x instead of just sine x? Is it equal to just cosine or negative cosine 2x? Okay, is it just equal to negative cosine 2x plus c? Well, the answer is no. This is not the answer. We will see later that there's more to this. Okay, so in these cases, this guy here and this guy here we will need a new method in integrating definite or indefinite integrals. That's our substitution rule. Recall from chain rule, if you have the composition function of f of g of x, okay, you get the derivative of this, you will end up with f prime of g of x times g prime of x. Correct? That's your chain rule. So what we're going to do is to integrate both sides of the equation. So we integrate this with respect to x. So integral of f prime of g of x times g prime of x dx. It's the same as integrating this guy here. So we integrate the derivative of f of g of x with respect to x. And remember, integral and thus the derivatives, which means that this is just your f of g of x. But because you are integrating, this is an indefinite integral, you should give a family of solutions. So you have here capital C. Okay? Now, we were able to derive this integral here on the left using the fact that we know the derivative of f of g of x with respect to x. Okay? But what if we are just given this guy here? What if we are just given this guy and we didn't recall that this left-hand side is actually a derivative of a composition function? So we will invoke our method of change of variable or the substitution. So from here, what we're going to do is to let u be equal to g of x. And we are using u. That's why commonly this is called the u substitution. You can use other variables. Of course, it should not be the same with your original variable. You can use t, you can use s, etc. You can use y, you can use z, etc. But commonly, we just use u. And therefore, you will have the u substitution. But anyway, if we let u be equal to g of x, then the derivative of u with respect to x, that's just your g prime of x. Or this du, if you think of du and dx as differentials, therefore you can separate them. Meaning the du, it will be equal to g prime of x dx. So what is this? You have this definite integral or indefinite integral, I should say, capital F prime of g of x times g prime of x dx. We let our u to be g of x. So this g of x here will be replaced by u. Okay? And therefore, our du equals g prime of x dx. This guy here, this g prime of x dx, that will be changed to du. So you will have this. And now if you look at this is simple integral of derivative. But this time with respect to the variable u. Okay? So if we integrate this simple f prime of u du, this is just f of u plus the arbitrary constant c. But then again, u, that's equal to g of x. So we bring back the original variable x. And u is equal to g of x. It means that this guy here will be f of g of x plus c. And now we're back to that composition function. So this is, okay, this is the substitution rule or this is the method of substitution. Okay? Take note, again, when we separated du and dx, we are treating them as differentials. Okay? So, the substitution rule for indefinite integrals. If u equals g of x is differentiable whose range in an interval I, if u equals g of x is a differentiable function whose range in an interval I, and f is continuous on I. This should be is. I think this should be is. Okay? So that the statement makes sense. So this guy here is. So if u equals g of x is a differentiable function whose range is an interval I, and if your f is continuous on I. So now the thing makes sense. Then, okay, integral of f of g of x, okay, times g prime of x dx, this is equal to f of u du. Take note of this, there is no f prime in here, okay? Unlike in what we did here, there was an f prime. That's why we were able to write this as f of g of x. In here, we don't have that f prime. So we stop at this particular statement, at this particular expression. Okay? And for the definite integral, so if g prime of x is continuous on the closed interval AB, and f is continuous on the range of u equals g of x, okay, then the integral of f of g of x, g prime of x dx from a to b, this is the same as the integral of f of u du, but this time here, the lower limit of integration is g of a, and the upper limit of integration here, it's g of b. So take note what happened in here, including the variable or the limits of integration. When you are doing substitution rule, okay, you change all those original variables to in terms of your new variable. Furthermore, you have your u here equals g of x. So this interval here, the interval AB is for the variable x. Here, we now have the variable u. So the interval must be for the variable u. Okay? And in fact, if in here, look at this AB here, this is actually x equals a and then x equals b. Okay? But your u is equal to g of x, and you have here du. So you need something u equals, but your x equals a and your u equals g of x. So at x equals a, u will be g of a. That's why we have g of a in here. Similarly in here, at x equals b, okay, your u becomes g of b. So this b here becomes g of b when you do the substitution. So you change all throughout. You just don't change this guy here and then you will put AB instead of G of A and G of B. And a lot of students do that. They use substitution. They change everything except these limits of integration. And then they evaluate using the original limits of integration meaning the interval for the original variable. They use that for the new variable, and that's where they will get the final answer wrong. Okay? Now, if you want to save, if you don't want the trouble of changing this limits of integration, what you can do is do the indefinite integral first. Take note that when you do the indefinite integrals, when you are able to evaluate this indefinite integral, you have to bring back the original variable x. And now, if you do that, okay, if you do that here, you do first the indefinite integral and you will get the general indefinite integral or the general antiderivative. You have the original variable, then you can use the original interval here. You can also do that. Okay? So let us use this new method that we just learned. Evaluate this integral of 1 plus 2x raised to 100 dx. So we can just let u be equal to 1 plus 2x. Okay? And then du, the derivative of 1 plus 2x, that's just 2 dx. Okay? Or we don't have a 2 in here. We have this statement, 1 plus, or we have this expression, 1 plus 2x raised to 100, and then we have the dx. So we can just solve for the dx. This means that your du over 2, or when we divide everything by 2, we have du over 2 equals dx. And with this substitution, this guy here will become the integral 1 plus 2x, that becomes u. So you have u here. And then the dx here, it becomes du over 2. So du over 2. So if we evaluate this is just 2, so you can bring it out. Okay, you can bring it out. It's just a constant. You will have 1/2. Sorry, I missed to write 1 raised to 100 in here. So this becomes u raised to 100. Okay. So if we evaluate this is just u raised to 101 divided by 101. Of course, plus the arbitrary constant c. And we bring back the original variable, your u, it's 1 plus 2x. So this guy here, it becomes 1 plus 2x raised to 101. And on the denominator, we have 2 times 101, that's 202, plus the arbitrary constant c. So this is now the integral of this 1 plus 2x raised to 100 dx. Next, we have sine 2x in here, and we want to integrate that. We can let u be equal to 2x, and then du, this is equal to 2 dx. And this guy here, this is just du over 2 equals dx. And therefore, with this substitution, we'll just have the integral of sine u, and then the dx becomes du over 2. So du over 2. So this is just, again, this is just constant. We can bring it out. So you have 1/2. And then this time, the integral of sine u with respect to u, that's negative cosine u, okay? And then plus the arbitrary constant c. And if we bring back the original variable x, we will have negative cosine 2x over 2 plus the arbitrary constant c. So this is now the integral. So it's not just cosine 2x. We have that denominator too. And it appeared because of the chain rule. Okay? Now let's have some more examples. We want to integrate square root of 2x plus 1. So one hint, which u to choose. You use or you take the u to be the expression that makes the integral complicated. So in this case, it's okay if you just have square root of x. We know how to deal with that. But this time here, we have square root of 2x plus 1. So 2x plus 1 makes this guy here complicated. In a sense, I mean quote unquote. So if we now let u be equal to 2x plus 1, the du, this is equal to 2x, to 2 du, or, 2 dx. What am I doing? So 2 dx. And then du over 2, this is equal to dx. So this guy here becomes the integral of square root of u. And then the dx becomes du over 2. Okay? Or if you're not comfortable working on this, you can write this in exponent form. You will have, let me put out the 1/2 outside of the integral there. You have 1/2 integral of u raised to 1/2 and then du. So in exponent form. So we can use the corresponding power rule, quote unquote. So for this, we just have 1/2 and then u raised to 1/2 plus 1 divided by 1/2 plus 1 plus the arbitrary constant c. 1/2 plus 1, that's just 3/2. And then we bring 2x plus 1 back. So in here you have 1 over 2, 2x plus 1 raised to 3/2 divided by 3/2 in here plus the arbitrary constant c. And if we simplify this, we'll just have 2x plus 1 raised to 3/2 divided by 3 plus c. Okay? Are we good? Next problem here. Now you have the integral of x over 1 minus x squared dx. Okay? It looks complicated at this point. You have the x, you have the radical. Okay? If this were just square root of x, then you can simplify this. But you have square root of 1 minus 9x squared. So at least we know that 1 minus 9x squared, that's the one that makes this integral complicated. So we can try that one. Okay? We can let u be equal to 1 minus 9x squared. If we get the derivative du or the differential du, we will have minus 18 x dx. Now, if you look at this, you have the x here and the dx. So you have your x dx. You have your x dx. You can bring this minus 18 to the other side. Meaning, you have du over negative 18. This is equal to x dx. So this x dx, it will be replaced by du over negative 18. So in here, we have the integral of 1 over square root of 1 minus x squared. But 1 minus, square root of 1 minus 9x squared. But 1 minus 9x squared, that's just u. So you have square root of u. And then your x dx here becomes du over negative 18. So if we convert this to exponential form, okay, we can rewrite this expression as including this guy here. So we can rewrite this whole expression here as negative 1 over 18 integral of u raised to negative 1 half du. Okay? Negative 1 half because originally it was the square root of u was in the denominator. On the denominator, it's u raised to 1 half. We bring it to the numerator, we get negative for the exponent. So if we integrate this, we will have negative 1 over 18 u raised to negative 1 half plus 1 divided by negative 1 half plus 1 plus the arbitrary constant c. Negative 1 half plus 1, that's positive 1 half. So negative 1 over 18 u raised to positive 1 half divided by 1 half plus c. We simplify this and we bring back the original variable. This is just negative quantity 1 minus 9x squared raised to 1 half over 9 plus the arbitrary constant c. Okay? So far, so good. Now, let's look at our next problem here. We now have a definite integral. So the integral from 0 to 1 of x over 4x squared plus 1 dx. So what I'm going to do here is to do substitution all the way. Meaning, I'll do substitution for this part. I will also replace the limits of integration. Okay? So, in here, if the denominator was 4x squared only, we can simplify everything and we can get the integral. But this was 4x squared plus 1. So, that's the one that makes this guy here complicated. So, we'll do the substitution. So, we let u be equal to 4x squared plus 1. Du will be 8x dx. And again, as you can see in here, you have the x, you have the dx. So you have here x dx. In here, you have 8x dx. So we bring this x again to the other side. Okay? So this will be du over 8. This is equal to x dx. Now, this is definite integral. We have to replace. So like I said earlier, I will do complete substitution. I will change the limits of integration. So in here, if x equals 0, then because 0 here, okay, if x equals 0, then u, this is equal to 4 times 0 plus 1. So u equals 1. If you replace this with 0, 4 times 0 squared, that's just 0, and then plus 1, so you have 1. If x equals 1, that's the upper limit of integration here, then you have u equals 4 times 1 squared plus 1, and this is equal to 5. Okay? So, complete substitution in here. This definite integral, take note, it's a definite integral. This definite integral is now equal to the integral. X equals 0 here, it's a lower limit of integration. The corresponding value for u must also be a lower limit of integration. So we put it here. 1 here, x equals 1, this is an upper limit of integration. So the corresponding value must also be in the upper limit of integration. So this is 5 here. And then you have now 1 over 4x squared plus 1. That's your u. 1 over u, I mean. So you have here 1 over u. And then the x dx will be replaced by du over 8. So you have here du over 8. So from here, okay, from here, we can bring out this 1 over 8. We will have 1 over 8 in here. The integral of 1 over u du, that's just ln of the absolute value of u. And since we did complete substitution here, I will evaluate this now at u equals 1 up to u equals 5. And evaluating, it's just the usual now. It's now the usual fundamental theorem of calculus second statement. So this will be 1 over 8 times ln absolute value of 5 minus ln absolute value of 1. So if we simplify this, ln of 1, that's just 0. So this is just ln of 5 divided by 8. So this is now the final answer. Okay? Like I said, common mistakes that students do. They don't change the limits of integration. They do this and they retain that those limits of integration, so 0 to 1. When they have this, they actually evaluate it at u equals 0 and then u equals 1. They actually do that, some of them. Okay? And that's wrong. Some will do this, okay? Some will do this. You have, they change this guy here. They do not change these limits of integration, okay? They do not change the limits of integration. They will end up with this, with the same limits of integration 0, 1. But then again, they add a next line here, bringing back the original variable. Okay? Of course, this guy and then the guy inserted in here, they are equal. That's totally true. However, this guy here up to this guy here with lower limits of integration 0 up to 1, okay, they are not the same. So what I'm saying is this integral from 0 to 1 of x dx over square root of, over 4x squared plus 1, this is not the same as the integral from 0 to 1 of du over 8u. They are not equal. Because, again, this 0 to 1 is for the variable x. When you do the substitution, the interval here also changes. It is not from 0 to 1. Okay? So, there's a question here. Why is there no plus c here? The reason is this is definite integral. You don't have to do the plus c thing. Is that good? There's no plus c in definite integral. Now, the next question, why didn't we plug in 4x squared plus 1 into ln of u? The reason is I can do the evaluation immediately here. If I'm going to bring back that 4x squared plus 1, then there's no point of doing this. Because once you bring it back, you will have to go back again to this interval. So it adds some steps. Okay? Okay, so let us go to our next problem here. Integral from 0 to 4 of x cubed square root of 1 plus x squared dx. Sorry, this dx should be outside this square root thing. Okay, so this guy here, so let me just edit it here. So there shouldn't be the dx. And then the dx must be in here. Oops. Okay. So we have this. Now, what I'm going to do is not the full substitution. Okay. So I will do only the substitution in here, and I'll not touch this interval. Meaning, later on I will go back to this interval. Okay, to this interval. So I will bring back the original variable x. Okay. In a sense, I can just work on. I just can work on the integral of x cubed times square root of 1 plus x squared dx. Okay? So from here, we do the substitution. Again, we can let u be equal to 1 plus x squared. Du, this is equal to 2x dx. Now look at this. I have x cubed square root of 1 plus x squared. Okay? This x cubed here, I can rewrite this as x squared times x. So if I'm going to rewrite this, we have the integral of x squared, square root of 1 plus x squared, and then I'll put the x beside the dx. So this x times x squared, that's your x cubed. So now I have this x dx, and I have it here. Furthermore, if we look at this, we will have u equals 1 plus x squared. So this guy here, 1 plus x squared, we will be able to change it to u. But we have this x squared here. We have to change this also in terms of u. And luckily, we can easily calculate this x squared from this. From here, you will have u minus 1. This is equal to x squared. And then in here, we have du over 2. This is equal to dx. And now we're ready to do all the substitution here. Integral. This x squared, it's u minus 1 coming from here. And then we have the square root of 1 plus x squared. 1 plus x squared, that's u. So in here, you have square root of u. And then x dx. Sorry, I missed the x in here. I just brought the 2 to the other side of the equation. So for this, we have the x dx. Okay? And therefore, what? This here, we have du over 2. And then this one, quote unquote, like looks complicated, but we can just distribute this square root of u to the sum here. You can treat u as u raised to 1/2. Okay? So you can just treat this u as u raised to 1/2, which means this guy here becomes the integral of u raised to 3/2 minus u raised to 1/2 all over 2. And then you have the du. And then you can bring these 2 here all the way outside. So if we evaluate this, we have 1/2. Okay? 1/2 quantity u raised to 3/2 plus 1 divided by 3/2 plus 1 minus u raised to 1/2 plus 1 divided by 1/2 plus 1 plus c. Okay? And then we now bring the original variable x here back to the situation or scenario. And we also simplify these additions or addition of constants. So I will have here 1/2 times quantity 1 plus x squared raised to 5/2 divided by 5/2 minus u, it's 1 plus x squared raised to 3/2 divided by 3/2, and then plus the variable, the arbitrary constant c. So in the previous step, in the previous example, I mean, we could have we could have done this. Okay? We could have completely substitute x in terms of u. So you can do this here. On the other hand, instead of doing that, the additional step I was talking about was this guy here. You bring it back. Okay? And then you can use the original interval in here. And notice, I have the plus c here, I have the plus c here. That's because I'm doing the indefinite integral in here. But once I use this here, this expression here into this, I can just drop that c out. Which means this guy here, this is now equal. We can distribute the 2 in here. So from this to this, if you distributed that, the over 2 here will be will disappear, will be cancelled. And so we will have 1 plus x squared raised to 5 halves over 5 minus 1 plus x squared raised to 3 halves over 3. Okay? This is the one that we evaluate from 0 to 4. Okay? So, like I said, it looks like there's an additional step, to be honest. Like, you bring back the original variable, it's actually, quote-unquote, an additional step in this part. But notice, in this solution, there is also an additional step. This guy here is actually an additional step in the usual. Usually, we just do this if we have the indefinite integral. For the definite integral, we add this guy here. Okay? But this is also a definite integral. However, we remove this part. The consequence is we have to do this part. Okay? So it's a give and take situation. Okay? So let us evaluate this. Let me adjust this whole part here. By the way, this guy here, it's part of your solution. So I have to see this if needed. Okay? And for you to get full marks. But anyway, so in here, equals at x equals 4, we will have quantity 1 plus 4 squared raised to 5 halves over 5 minus 1 plus 4 squared raised to 3 halves over 3. Quantity minus at x equals 0, we just have 1 plus 0 squared. That's just 1. And then you raise it to some power, it's still 1. So this is just 1 over 5 minus 1 over 3. And then just simplify this. You will get, so 4 squared, that's 16. So you will have 1 plus 4 squared, that's 17. So 17 raised to 5 halves over 5 minus 17 raised to 3 halves over 3. Quantity minus 1 over 5 minus 1 over 3. So you may leave the final answer in this form here. Okay? Questions? Now, let us look at our next example here. Okay? We want to integrate x square root of 1 minus x squared dx from 0 to 1. So, here, let's just have let u be equal to 1 minus x squared. du equals minus 2x dx. And I have x here and dx in here, so I just need the x dx. So we will replace dx, or we will change this equation into du over negative 2 equals x dx. I'll do full substitution. Okay, I'll do full substitution. Lower limit of integration, that's 0. So x equals 0 implies u equals 1 minus 0 squared. So that's 1. X equals 1, that's the upper limit of integration here, implies u equals 1 minus 1 squared. That's equal to 0. Therefore, we have now the integral. Take note, x equals 0, this is a lower limit of integration. The corresponding value for u, it's 1. So this is 1. In here, you have x equals 1. That's the upper limit of integration. The corresponding value for u, it's 0. So here we have 0. And then what? We have the square root of 1 minus x squared. That becomes square root of u. And then x dx, that becomes du over negative 2. So we have here du over negative 2. Okay? So if we do the integration, we can bring negative 2 out. So we will have negative 1 half. And again, this square root of u, you can use u raised to 1 half. So that will become u raised to 1 half plus 1 divided by 1 half plus 1. We evaluate this. Take note of that. Since I have changed the limits of integration also, we evaluate this from 1 to 0. So in here, what do we get? We have negative 1 half at u equals 0. Okay, at u equals 0, this is just 0. So we have 0. Minus, at u equals 1, we have here 1 over 1 half plus 1, that's 3 halves. So 3 over 2. So if we simplify this, we distribute this negative 1 half, negative here, it becomes plus. The 2 here will cancel the denominator of the denominator here. So we'll just get 1/3. So this is the final answer. Okay? Questions? All right. Now, let us look at some theorems. So as I have mentioned at the beginning, we will add more formulas in the set of formulas that you currently have. So we'll have the integral of tangent x dx. We'll also have the integral of cotangent x dx. We will have the integral of secant x. And we will have the integral of cosecant x, which is given this, as this here. For the secant x, it's this guy here. For cotangent x, it's this guy. And then for the tangent x, it's this guy here. So for this, I will prove this statement here and also this statement here. And then for you have to show 2 and 3. Okay? You'll get a hint. Okay, you'll get a hint or hints. You'll get hints how to calculate this or how to derive this. So that's proving. Although you know what to expect, that's still proving. Okay? So for number 1, we have the integral of tangent x dx. What we are going to do is to rewrite tangent x as sine x over cosine x. And now, we do the substitution. Let u be equal to cosine x du. This is equal to what? This is negative sine x dx. So in here, you have the sine x and then the dx. You have that. You don't have the negative, so you put the negative to the other side of the equation. Therefore, sine x dx, it will be replaced by negative du. And then your cosine x, it will be replaced by u. So this guy here, it's just the integral of negative du over u. Okay? And then what is this? This is just your logarithmic function. So equals negative ln absolute value of u plus c. But when you have a negative coefficient of your ln, okay, you can make it as an exponent of the guy here. So this guy here, it's ln absolute value of u raised to negative 1 plus c. And then you can bring this exponent negative 1 inside the absolute value. So you will have ln absolute value of u raised to negative 1, then plus c. And then you bring back u, that's just cosine x. This is ln absolute value of cosine x raised to negative 1 plus c, but cosine x raised to negative 1, that's your secant x. Take note, negative 1 here, it's an exponent. It is not the inverse notation. This guy here is an exponent. So this one here, it's 1 over cosine x. And that's where the secant x will appear. So you have this formula in here. Okay? So that's for the tangent, the integral of tangent x dx. For the second one, you do the same. You have cosine over sine. Then you do the same substitution. You have to expect which one to use. And then you'll be able to derive this easily. Let us do number 4. So this is done. We are now going to do this. So in here, there is a trick. So you have the integral of cosecant x dx. The trick here is to multiply and divide by cosecant x minus cotangent x. So you have the integral of cosecant of x. We multiply by cosecant of x minus cotangent of x. And then we divide with the same thing. Cosecant of x minus cotangent of x. And of course, we have the dx. So they are equal because, well, this will cancel this one. So you are just multiplying by 1. Okay? Now, we just distribute this cosecant x to this guy here, we will get integral of cosecant squared x minus cosecant x cotangent of x divided by cosecant of x minus cotangent of x, and then you have your dx. And then from here, you can now let u be equal to cosecant of x minus cotangent of x du. This is equal to derivative of cosecant of x. That's negative cosecant of x cotangent of x minus derivative of cotangent of x, that's minus cosecant squared of x. And this, everything here, this is multiplied to dx. But in here you have cosecant, you have negative times negative. So you got cosecant squared x. That's positive. And you have minus cosecant x cotangent x. That's precisely this denominator here. So if you continue with the substitution, this is just the integral of 1 over u du. And this is ln, absolute value of u plus c. And therefore, you have ln absolute value of cosecant of x minus cotangent of x plus the arbitrary constancy. So this is the expression that we are looking for. So that's for the integral of cosecant x dx. So as a hint, for your secant x, you expect secant x plus tangent x as a denominator. So you multiply and divide the secant x by this expression, secant x tangent x, and then you do the substitution, just like this guy here. The solution is very similar to this. Okay? Questions? Now, one last set of theorems. Okay? Suppose f is continuous on the closed interval, negative a to a, for a greater than 0. Okay? If your function f is an even function, it means f of negative x, that's equal to f of x for all x from negative a to a. Then the integral of f of x dx from negative a to a, this is just equal to twice the integral from 0 to a of f of x dx. So it's like there's a symmetry. Okay? So you just do half of that. And then you just multiply to 2 to get the whole thing. Okay? This guy here, this is symmetric with respect to your x-axis. The function, the even function, it's symmetric with respect to x-axis. On the other hand, if f is an odd function, meaning f of negative x equals negative f of x, then if you integrate from negative a to a, or the function f of x dx, you'll always get 0. Okay? So this function here, this is symmetric with respect to the origin. Okay, this is with respect to the origin. And you'll see, if you have some even function, if you have some odd function, you will definitely get this identity here. For example, here, integral from negative 1 to 1 of tangent x over 1 plus x squared plus 2x to the 6 dx. Okay? This guy here, your tangent function, it's an odd function. The denominator here, it is an even function. As a whole, this is an odd function. So you have to check this guy here. Try to check this. Try to verify that this is true. Okay? So if you were able to verify this, then you know that this integral here, this is just equal to 0, according to this theorem. Okay? In here, you have the integral from -3 to 3 of x to the 4 minus 3x squared minus 5 dx. This guy here, this is an even function. So it's on this case here. Okay? So instead of doing the whole thing, you can just do half. So from 0 to 3, and then you multiply it to 2. Okay? And you will get your answer. For polynomials, for example, this guy here, it's good that your lower limit or your upper limit, or at least one of them, is 0. The reason is when you evaluate the polynomial after integrating, everyone will have x. Okay, after integrating. So at x equals 0, that will disappear. You'll only need the one which is non-zero. So this is helpful also. Okay, so try to work on this. Here, you just need to verify this guy here, and once you've verified, you will get 0. Okay? So, I think that's it from me for today. That's the last. So I hope you can work on the exercises or the ones that I want you to verify or calculate when you have time. So you will be able to practice. Okay? So thank you for staying and have a great evening.